Good evening, my fellow scientists. It is Sunday, April 22nd, 2018. It's been a bit of a crazy week here in the Allen lab, but I'm going to give you a quick update on the battery. For those of you who are new, we've been working for the last year on generating an all-iron battery with an iron anode there on the left, which gets oxidized to iron 2, and then iron 3 accepts that electron, gets reduced to iron 2, and on the far side, that happens at a carbon cathode. Now, we've tried a whole bunch of different designs. The most successful was this 50 milliliter tube cell, which was able to light up an LED. That was, 8 or 9 months ago. Since then, we've built a bunch of different kinds of cells, including this pouch cell, where we have an iron anode made of steel wool and that carbon cathode, building a separator out of paper and polymer. But ultimately, what it all comes down to is this charge-discharge cycle, where we charge it up, which is where the line goes upwards, and then discharge it when the line goes downwards. And we measure how reproducible that is and whether it degrades the battery and how much energy gets stored. For the last 2 or 3 weeks, we've been working with this type of cell, little galvanic style cell, in which we have an anode solution of various kinds and a cathode solution of various kinds, and we've been using this to try to get a clear comparison, since all the cells are set up the same way with the same beakers and the same felt cathode, so that we can compare a bunch of different chemistries acting as either side of the battery. This week we've been doing sulfate, so iron goes to iron oxide, hydroxide, and or iron sulfate at the cathode, and then at the anode, iron 3 sulfate gets reduced to iron 2 sulfate. The charge-discharge cycle looks like this graph on the right. Looks a little uneven, but the amount of current it's actually delivering is a lot larger than any of the other batteries we've tried. It's about 0.5 milliamp for this little cell. You can also see that the overall charge was not being fully reversibly charged by the 1.4 volts charging voltage, so that charge state goes down over time. That means that we really can't assess the coulombic efficiency with these settings, but it does tell us that this battery is holding a lot of coulombs. Right there, it's holding almost 10. The discharge to 0 is still going on, so I know it's more than 18, but I don't know how big it is yet, but it's way bigger than any other cell we've tried. The open cell potential is also the highest. Here's the summary. Sucrose and sulfate have are close, but sulfate wins on open cell potential. Coulombic efficiency, we don't know because it's too good for these settings. We need a higher charging voltage to really establish that. But it's definitely better than EDTA or fructose, which are holding in it at 50 to 80%. And then the capacity is definitely the biggest so far. What's really surprising is that the sulfate cell has clearly generated some kind of precipitate, some nanoparticles or microparticles that are hanging out in suspension, which is not the case for any of the other chemistries we've tried. So we shall see how that affects the capacity going forward, but for now, sulfate's winning. Thank you very much for tuning in, and special thanks to Nico and Ricardo for their hard work this week getting this done. We will hopefully be able to round out our trials of different chemistries next week and move on to starting optimizing some electrodes. If you like iron batteries, renewable energy, and science, stay tuned every week to the Allen Lab.